what I'm going to talk about today is accelerating scientific computing using InfiniBand DPUs, or data processing units. Part of our NVIDIA has a platform that we refer to as the cloud native HPC platform. It's in the process of being developed. And from a network perspective, that platform plays a role in several different areas of the platform as a whole. One, it has what we've done on the InfiniBand side of things for ever since the inception of Mellanox InfiniBand, was support for in-network computing. That is offloading portions of network processing to the network hardware. There's work being done on zero trust security, performance isolation, isolating one application from the other, computational storage, as well as enhanced telemetry. So from a product perspective, from a hardware perspective, the pieces of the network pieces that contribute to the stack include the switching infrastructure, the quantum switches, the ConnectX NICs, smart NICs, the BlueField data processing units, the DPUs, as well as also Ethernet support for Ethernet switches, the Spectrum line of support, and software to manage and monitor the network and applications. So UFM and NetQ are those particular pieces. So from a hardware from an HPC performance perspective, there are several problems, general areas that people struggle with or battle against, and to be able to get good scalability, good performance at scale. And these include making it possible to overlap computation and communication, dealing with load imbalance within the application. So you have typically applications that's very common for real world applications in the area of HPC to have a load imbalance. There's jitter that causes system jitter that causes again performance degradation in the application, and there's interference from multiple jobs running in parallel and competing for the same network resources. So from a DPU perspective, the DPU plays a role, or BlueField plays a role in addressing each of these areas here. So with I'll talk a bit about the DPU. We'll describe it a bit here in a little while, but just the important feature here is the DPU runs asynchronously to the host. And so it has the ability to make decisions asynchronously relative to the host. And so it can certainly supplement these sort of abilities to overlap computation and communication. The in-network computing work that's done on the DPU, again, I'll talk about more what BlueField is here in a little while. It allows one, I'll show real examples, to deal with some of this load imbalance in the applications under some scenarios, specifically when certain type of collective operations are in play. Jitter is dealt with actually by moving some of the management work from the main host to the CPU. I mean to the DPU. I'm sorry. Things like security management, things like potentially I/O forwarding and the like, the DPU is also very good at helping improve the ability to be rather responsive with congestion control. So the BlueField data processing unit. So this is a very generic slide of BlueField, not referencing, sort of referencing, but not exactly referencing a particular generation technology, of InfiniBand technology. So the BlueField is used to supplement, currently used to supplement in 3 different areas. One is the software-defined networking, software-defined security, as well as software-defined storage. And the focus of my talk today is going to be on the area of software-defined networking. So the BlueField itself, there's a cartoon of what a BlueField looks like on the right-hand side of the screen. What it is a system on a chip. It includes programmable ARM cores. It includes a ConnectX network core, memory that the ARM cores can use, switch so that one can direct traffic either to the host or either bypassing the DPU, the ARM processors, just having the system on the chip be a network adapter, or traffic can be routed to and from the ARM memory, and then the ARM cores can process it. It also has several acceleration engines. Depends on what generation you are as to what sort of accelerators that exist there. You have, for example, a very strong regex engine that's aimed mostly at security. I think I've covered most of the capabilities. Another capability that I didn't mention is there are also some RISC-V programmable cores that exist. They're actually part of the ConnectX core that sits on the BlueField. And so those can be used to mostly for coordinating activity between different flows. So they have the ability to post operations to the network adapter, handle completions, run some user definable logic there. And so there's not a lot of memory bandwidth going into those cores, and so they're really good for those sort of metadata operations or meta-level operations. So there are 16 in BlueField 3, and I'll get to what those devices are here soon. There are 16 of those RISC-V cores. Each of them runs 16 hardware threads that can be used. They are actually in the data path, as opposed to the DPU, to the ARM cores, which are not in the data path. So from a platform perspective, there are 2 parts to it. Like on any platform, there's the software side of things, which is encapsulated in what we call our Doka SDK. It includes support for things like security, networking, and storage, as well as acceleration libraries. It has tools there that it has capabilities there that users can take and use to help develop code that they may want to run on those ARM cores. It also comes with orchestration, management, and telemetry services, all as part of this SDK. This is about as much as I'm going to say today about the software set of things. The focus is going to be mostly on the hardware set of things and how we use this given hardware to accelerate HPC applications. So we're in currently the beginning of the 3rd generation of these DPUs, BlueField 3. BlueField 1 came out, I don't remember, 5, 6, 7 years ago, a while back. BlueField 2 has been in use for several years, 4 years, or at least 4 years, and BlueField 3 is emerging. So a few things about the BlueField, in both differences as well as some base capabilities. So network bandwidth is a network bandwidth at a given generation of technology of the given generation of technology that the DPU happens to belong to. So the BlueField 2 was part of the HDR generation of technology, so it supported 200 gigabits per second, Ethernet, and InfiniBand, not just InfiniBand. BlueField 3 is part of the NVR generation of technology, so 400 gigabit per second. The network bus, BlueField 2 supported PCI Gen 4. BlueField 3 supports PCI Gen 5. Message rate that's reflected here is a message rate of the ConnectX core, so about a 50% bump in message rate going from BlueField 2 to BlueField 3. The compute capabilities go from, as measured by SpecInt, go from 9.8 up to about 17 from BlueField 2 to BlueField 3, so it's capable of doing more operations. A few things about the ARM CPU. So the ARM CPU is not a server class CPU. That's not its intent. It's intended to be more as something that one could run when it's plugged into a PCI slot with or without some additional power. So there's certainly versions that run with just with the 75 watts that you can get from the PCI slot. There are some versions that are a little more beefy that require some additional power. BlueField 2 had 8 programmable ARM cores, A72s. BlueField 3 has 16 A78s. Memory bandwidth takes a substantial increase going between BlueField 2 from BlueField 2 to BlueField 3. So going from 17 gigabytes per second up to 80 gigabytes per second. So the reason this is relevant in the context of network operations, because at BlueField 2, you could not saturate the wire with data originating from the DPU memory. You could from data originating from the host, but not data originating from the ARM cores, ARM memory, I'm sorry, but in BlueField 3 you can. In BlueField 3 you have some additional spare memory bandwidth that you could potentially use to do some operations and hope to be able to pipeline and maintain high network bandwidth. Having said that, and I'll come back to this again, that does not mean that if you use BlueField 2 or BlueField 3, because all the results I'm going to show now are BlueField 2 results, that doesn't mean that you can't achieve network bandwidth with network operations in which the DPU, the BlueField 2 is involved. And I'll talk about that very, very soon. So in terms of the cloud native supercomputing infrastructure, it's a full infrastructure providing bare metal performance to the system with the DPU in use. It has orchestration tools and the like for orchestrating both the host side and the DPU side, as well as network monitoring and capabilities and like. And these network capabilities plug into a wider set of monitoring tools. And of course, every vendor has their own favorite tools. So these tools are set up such that you can use the ones that you want, not necessarily use the ones that you want, and not necessarily use the ones that you have other things that you prefer to use. Sort of a generic slide, just talking about software layers. So when we look at accelerating HPC applications, our view is really one of trying as much as to the degree possible to accelerate existing applications that are already using existing system capabilities by modifying lower level layers. It's not always possible. Like with any system, when you have new capabilities, sometimes you get better. You're able to do more if you're willing to change. But currently there's work going on in changing UCC, which is an open source collectives operation library, UCX, which is an open source point-to-point communication library. There's work in the area of storage. Performance isolation really talks about congestion control, but also some QoS, as well as orchestration tools. And Doka is the SDK that we use to deliver all these things and enable the DPU. So I'm going to switch gears a bit and start talking a bit about how one uses how we've used the DPU to accelerate communication libraries. So I have a team that's been working on this for a little over a year. Our focus has been on accelerating collective operations, specifically blocking collective operations, because those are the ones that are most commonly in use. And so that's where we put our effort. And when we started out this effort, we weren't quite sure how we would be able to accelerate blocking operations, but we did learn things in the process, and did learn, and I'll talk about that here soon, and show that these sort of things are possible. So from a software perspective, the way we view the DPU and the system is the DPU is paired with a host. We list a CPU here. It doesn't have to be a CPU. It could be also a GPU or something else. So we have each host has associated with it a BlueField DPU. Now we're going away from that, so we can do some things that are a bit more general. But this is where we've started. So a few things about this view that are very relevant in terms of trying to decide how to partition work for in this case in the collective communication. So we assume the work that we've done so far has been in the context of MPI. So we assume some number of MPI ranks running on each host, and some number of what we call asynchronous agents or service processes. I mean, we call them service processes. They're asynchronous agents that run on the DPU and have access to the network. A few things are important to note here. So I did make the comment that we have an association, generally an association between a CPU and a service agent. Each service agent serves multiple MPI ranks. So this is because typically one has about an order of magnitude more cores on the host side than you have cores on the DPU, and so you don't want to make an assumption that had a one-to-one assumption between capabilities on cores on a CPU and cores on the DPU. And that brings some interesting opportunities, because it actually gives us a broader scope on the DPU side of actual traffic that's going on in the system. We're sort of forced to a model like that, and that model actually exposes communication in a way that's not exposed on the host. We have access to things that we just typically don't have access to on the host, so it helps us from a network utilization perspective. Also, we don't assume that because we have a DPU, all the work that's going to be done, if we offload the algorithm, it's all offloaded to the DPU. We really, depending on the type of collective operation, currently we distinguish between blocking and non-blocking operations. For blocking operations, we'll split the work between the host and the DPU to enable the most efficient overall solution performance. And for non-blocking, since the focus there is to overlap, we'll move all the work down to the DPU as quick as possible. Doesn't necessarily always get as good performance, but it allows you the overlap that's really critical. From a communication perspective, MPI processes continue to interact with other MPI processes. The service processes can exchange data within themselves, both locally and remote. So we're not restricting by any way the way in which communication goes on. One of the capabilities that we take advantage of that's really helped, even in BlueField 2, get high performance, get good network bandwidths, and good application acceleration, is a capability called cross-Gavami, which lets the DPU post network activity on behalf of data that's host resident. And so if you're interested in moving data, you don't have to actually be able to access that data with read-write type of activity to send the data. The BlueField can initiate data transfers on behalf of data that's host resident, which means it can happen asynchronously. You don't have to wait for a time slice to do your progress. So from a cartoon perspective, this is an extremely high-level view of how one looks at how we implement collective operations. So generally, when a collective operation is called, there's a notification that goes from the host to its paired service process on the DPU, and that's where, depending on your algorithm, depending on the algorithm is exactly what happens. That's where the DPU starts to get involved in the application. And one of the things the DPU does is initiate, at least in the collectives that we've implemented, is initiate data transfer. So initiate, for example, either a RDMA write, RDMA read, whatever, from data that is resident on rank 0 that's on one host and transfers it to rank 1 that's on a different host. Again, without any intervention from either host. And then at the end, of course, when all the operations are done, the DPU will notify the host that it's done with its work, and things can proceed. So a bit about performance. So the collectives that we focused on have been collectives that we can, well, one, they were selected because they were used by important applications in bids. Two, they also had involve data transfer. Those particular applications also involve transferring medium to large size data. So specifically, the collectives that we focused on so far have been all to all V, all gather V. And what we've this figure here shows latency as a function of number of hosts in the job for host only implementation, which is in gray, and DPU offloaded implementation, which is in green. We list the latency here for both one process per node, so we're only utilizing one process on each node, as well as full processes per node. In this case, it was 32 processes. And we see that we do get very good performance with a DPU offloaded version of the implementation. We also measured this data for the non-blocking all-to-all V operation. The differences between blocking and non-blocking look bigger here, just for the same configuration I described before. Just to be brief and clear, the actual performance of the all-to-all V, the actual latency, is the same as it was for the blocking. The difference in performance here is really a difference in performance in implementation of the non-blocking collectives, because those typically, since they're used so infrequently by applications today, there's usually not a lot of effort put in to optimize those. We also measured computation communication overlap capacity. We've shown that so again, green means DPU offloaded, gray means host only. As expected, since the DPU runs a collective completely asynchronously, it has very high capacity, close to 100% capacity to overlap communication and computation, whereas the host versions really don't do a good job, but that's not surprising at all. So putting this all together, at the end of the day, the target is not to have these amazing performing collectives. I would actually take less performant collectives if I could get better application performance. But at the end of the day, what matters is the impact on applications. And so we've used these offloaded libraries for three us and others, I should say. This is some of this work of Octopus and GSAM is our work. The FFT data reported here is work from OSU. So we've seen nice performance improvements in applications when we also use these libraries, these offloaded live capabilities. So that's all I have, and be glad to answer questions.
Okay, great. Do we have any questions? Okay, very cool. Well, thank you very much, Richard.